Unit 2, Minerals and Rocks. Lesson 1, Properties of Minerals. After this lesson, we'll be able to define a mineral, explain how minerals are identified, and explain how minerals form and where mineral resources are located. My Planet Diary blog, posted by Mackenzie from Brewerton, New York. I used to go to summer camp. We went on a good field trip to an underground cavern. When we got inside, I thought I was in a dragon's mouth. Later, I found out that those teeth were stalactites and stalagmites. Stalactites hang from the ceiling, and stalagmites grow from the ground. If you are ever in the wizarding world and you have to ask Hagrid, hey, what's the difference between a stalactite and a stalagmite? And he does not know the answer because he did not know the answer when he talked to Harry. Stalactite with a C hangs from the ceiling, also with a C, and stalagmite with a G grows in the ground. What's up with this? Stalactites and stalagmites are usually made up of the mineral calcite. This mineral dissolves easily in acidic water. How do you think calcite hardened to form the features in the cave? Well, potentially the acidic water that was in the cave that had contained the dissolved calcite, and then the water evaporated, leaving the calcite behind. It's like if you put a bunch of salt into a glass of water, and the water evaporates, you're gonna be left with some salt. What is a mineral? Look at the two substances in figure 1. On the left is a hard chunk of coal. On the right are beautiful quartz crystals. Both are solid materials that form beneath Earth's surface. But which is a mineral? How are minerals defined? A mineral is a naturally occurring solid that can form by inorganic processes and that has a crystal structure and a definite chemical composition. For a substance to be a mineral, it must have all 5 of these characteristics. So, is either quartz or coal a mineral? Here are the 5 characteristics that a substance must have to be a mineral. It must have all 5 of these, not just 4, all of them. The first one is naturally occurring. All minerals are substances that are formed by natural processes. Quartz forms naturally as molten material called magma cools and hardens beneath Earth's surface. Coal forms naturally from the remains of plants that are squeezed tightly together. The second one is it forms by an inorganic processes. All minerals must be able to form by inorganic processes. That is, every mineral must be able to form from materials that were not a part of living things. Quartz can form naturally as magma cools. Coal comes only from living things, the remains of plants that lived millions of years ago. But some minerals that can form from inorganic processes may also be produced by living things. The third is solid. A mineral is always a solid with a definite volume and shape. The particles that make up a solid are packed together very tightly, so they cannot move like the particles that make up a liquid. Coal and quartz are solids. The fourth is a crystal structure. The particles of a mineral line up in a pattern that repeats over and over again. The repeating pattern of a mineral's particles forms a solid called a crystal. A crystal has flat sides, called faces, that meet at sharp edges and corners. The quartz in figure 1 has a crystal structure. In contrast, most coal lacks a crystal structure. And the fifth thing it must have is a definite chemical composition. A mineral has a definite chemical composition. This means that a mineral always contains certain elements in definite proportions. An element is a substance composed of a single kind of atom. Quartz always contains 1 atom of silicon for every 2 atoms of oxygen. The elements in coal can vary over a wide range. Here we have figure 1. Are they or aren't they? To be classified as a mineral, a substance must satisfy 5 requirements. So let's complete this checklist. Are quartz and coal minerals or only naturally occurring substances? Well, the first thing that a mineral must have is to be naturally occurring. We know because we read up at the top that quartz forms naturally as molten material called magma pools, and coal forms naturally from the remains of plants. Perfect. Check them both. The second has to be can form by inorganic processes. So it has to be made up of things that were not part of living things. Quartz, as we know, can only form as magma pools. So that's inorganic. Yup. My check is going to be next time. Coal, on the other hand, forms naturally from the remains of plants. Plants are living, so it's not an inorganic. It's not inorganic. The third thing it has to be is a solid, not a liquid, not a gas, not anything else. It has to be a solid. Well, quartz, we can hold it. It's pretty packed together tightly, cannot move. As well, that is a solid. Coal is also a solid. Have a crystal structure. That's the fourth thing it must have. So the patterns must repeat. The particles line up in a pattern that must repeat over and over again. We can see a picture of our quartz. Yup, looks like it's crystallized. Looks like it has the repeating pattern going over and over again. Our coal, on the other hand, kind of just looks like a blob. Not much is repeating. Nothing really looks crystallized. And the fifth thing it must have is a definite chemical composition. Again, meaning that a mineral always contains certain elements in definite proportions. They said that a quartz always contains 1 atom of silicon for every 2 atoms of oxygen. That means no matter what size, what shape, what color, a quartz is going to have 1 element of silicon for every 2 atoms of oxygen. That's its ratio, 1 to 2. It's always going to be 1 to 2. Boom. On the other hand, coal can vary. It can be 1 of whatever to 2 to whatever. It can be 13 to 17. They don't go together. It's not a repeating process, repeating. It can be whatever. So the only way for a mineral, or for a substance to be classified as a mineral, it must have a check mark in every single box. We can see that quartz does. So quartz is a mineral. Coal only has 2 things checked. It needs to have all 5. So coal is a naturally occurring substance, but is not a mineral. Almost all minerals are compounds. In a compound, 2 or more elements are combined, so that the elements no longer have distinct properties. For example, the mineral cinnabar is composed of the elements sulfur and mercury. Sulfur is a bright yellow color. Mercury is a silvery liquid at room temperature, but cinnabar has solid, shiny red crystals. Different minerals have a different combination of elements. For example, a crystal of quartz has 1 atom of silicon for every 2 atoms of oxygen. This ratio is constant for all varieties of quartz. Each mineral in the garnet group of minerals has 3 atoms of silicon for every 12 atoms of oxygen. But garnet also contains other elements in set ratios. Figure 2 shows only 1 variety of garnet. Some elements occur in nature in a pure form and not as part of a compound. Elements such as copper, silver, and gold are also minerals. Almost all pure solid elements are metals. So down here we have a picture of a rose quartz. This one is pink. It doesn't look like the quartz that we saw on the page prior. but we know it is quartz. It has one atom of silicon for every 2 atoms of oxygen. We also have an almandine garnet. Many different types of garnets, as they said, this is just one type of garnet. So this does have 3 atoms of silicon for every 12 atoms of oxygen. How are minerals identified? Geologists have identified more than 4,000 minerals, but telling these minerals apart can often be a challenge. Each mineral has characteristic properties that can be used to identify it. We have color. Is all that glitters really gold? Both minerals shown here are golden color. We're going to think, as I read, which one, A or B, do you think is actually gold? Both minerals shown here are the color gold, but only one is the mineral gold. In fact, only a few minerals have their own characteristic color. A and B, A and B. Which one do you think is actually gold? The answer is A. So this first one here looks kind of like buttered popcorn, kind of smushed together, like a Rice Krispies popcorn ball. That's gold. B is called pyrite. Fool's gold. It's what tricks you into thinking, this is gold! I'm rich! And no, sorry, it's not. It's pyrite. Next thing we have is the streak. The streak of a mineral is the color of its powder. Although the color of a mineral can vary, its streak does not. However, the streak color and the mineral color are often different. For example, pyrite has a gold color, but its streak is greenish black. So if you take letter B up at the top, and they have a specific little block that you can rub these little minerals on to find out what it is. If you rub it on there, it's not going to show up gold, it's going to show up greenish and black. And that is a way to figure out, do you have gold or do you have pyrite? Figure 4 says, the color of any particular mineral streak does not vary. Which do you think is more useful in identifying a mineral? The mineral's color or the mineral's streak? I would say the mineral's streak, because no matter what, if you have 3 different types of quartz, they're all going to have the same streak color, but they might have different actual colors. Like we have our rose quartz in the picture. Luster, that's our next one. Luster is a term used to describe how light is reflected from a mineral's surface. For example, minerals such as galena that contains metal often have a metallic luster. Quartz has a glassy luster. Other terms to describe luster include earthy, silky, waxy, and pearly. It says geologists use many terms to describe the luster of minerals. It says choose any item in your classroom that reflects light. In one word, describe its luster. So, I guess my example is, if you have a pencil nearby, so I have one right here, and you see the pencil lead, it's reflecting light, but it's not reflecting in a way that's kind of metallic-y, and it doesn't really look very silky like malachite. It looks more like talc at the bottom, so this we would probably say is a greasy. The luster for a pencil lead would be When you want to identify a mineral, one of the most useful clues to use is the mineral's hardness. In 1812, Austrian Friedrich Mohs, a mineral expert, invented a scale to help identify minerals by how hard they are. The Mohs hardness scale is used to rank the hardness of minerals. The scale assigns a mineral's hardness a ranking from 1 to 10 as shown in Figure 6. Hardness can be determined by a scratch test. A mineral can scratch any material softer than itself, but can be scratched by any material that is harder. For example, suppose you found a deposit of azurite because you just happened to find azurite in your backyard. Azurite is not on the Mohs scale, but you would like to determine its hardness. So you take a small sample and try to scratch it with talc, gypsum, and calcite. But none of these minerals scratch your sample. Apatite, rated 5 on the scale, does scratch it. Therefore, the hardness of azurite is probably about 4. Example 2.0. Let's say we're trying to find out the hardness of pencil lead. We know the hardness of a fingernail, which would be 2.5 on the Mohs hardness scale. And we know a copper penny, 3.5. Or 3.0, sorry. If you take your pencil and you scratch your fingernail, you'll probably get a line of, the pencil lead that's left behind, but you won't get a scratch mark on your finger. So we know, our pencil lead must be less than your fingernail. And if you take your fingernail and you scratch the pencil lead, you're going to put a little mark in the pencil lead. It might not be very noticeable, but you can see a little scratch mark on it. So at some point, the pencil lead is going to be less than a 2.5 on the Mohs scale. I'd say it's probably about maybe a 1 or 1.5. And as much as I would love to do figure 6 alongside with you, this is like a brain puzzle. Thinking back to, if you remember when we did the Who Owns the Fish? If Rob lives in the purple house and Amelia has a cat and Ronald likes to drink milk. It's kind of like that. But this time we're placing topaz, gypsum, apatite, diamond, and quartz on our scale of increasing hardness on the Mohs scale. So this is in your worksheet. Each mineral has a characteristic density. Recall that density is the mass in a given space, or mass per unit volume. No matter how large or small the mineral sample is, the density of that mineral always remains the same. For example, the density of quartz is 2.6 grams per cubic centimeter. Always. The density of diamond is 3.5 grams per cubic centimeter. Always. To measure density, geologists use a balance to first determine the precise mass of a mineral sample. Then they place the mineral in water to determine how much water the sample displaces. The volume of the displaced water equals the volume of the sample. The mineral's density can then be calculated using the formula below. Density equals mass divided by volume. We've done this before. You can compare the density of 2 mineral samples of about the same size. Just pick them up and heft them, or feel their weight in your hand. The sample that feels heavier is probably also denser. The atoms that make up a mineral line up in a regular pattern. This pattern repeats over and over. The repeating pattern of a mineral's atoms forms a mineral's crystal structure. All the crystals of a mineral have the same crystal structure. Scientists can use crystal structure to identify very small mineral samples. For example, scientists can bounce a powerful beam of particles off very small crystals. Because the atoms that make up minerals line up in regular patterns, these beams produce distinct patterns of light. As shown in Figure 7, different minerals have crystals that are shaped differently. Halite crystals are cubic, that is, they are shaped like a cube. You can break a large piece of halite into smaller pieces, but the smaller pieces still contain crystals that are perfect cubes. Geologists classify crystals by the number of faces, or sides, on the crystal. They also measure the angles at which the faces meet. So first up, what 2 features do geologists use to classify crystals? Well, the number of faces and the angle at which those faces meet. Does a quartz crystal have more or fewer faces than a halite crystal? Well, as we see our halite and we count them, 1, 2, 3, 4, 5, 6 faces. Quartz, 1, 2, 3, 4, 5, 6, 7, 8 faces. Which one's bigger? 8. So quartz has more faces than a halite crystal. You may be familiar with how the mineral mica can be split apart to form flat sheets. A mineral that splits easily along flat surfaces has the property called cleavage. Whether a mineral has cleavage depends on how the atoms in its crystals are arranged. The way atoms are arranged in mica allows it to split easily in one direction. Figure 8 shows cleavage in mica. Most minerals do not split apart evenly. Instead, they have a characteristic type of fracture. Fracture describes how a mineral looks when it breaks apart in an irregular way. For example, when a quartz breaks, it produces curved, shell-like surfaces. So we see, onto the next side, we cut a piece of mica and it makes a nice little line. It splits super easily. It's like tearing your paper, and it tears like so perfect, and you're like super happy. Fracture, the quartz kind of looks more like a ball. It doesn't quite look like it cut that easily. It's like when you try to rip your piece of paper and you just yoink it and it like rips in a curve, and you're like, half of my work is still in the book and half of it's in my hands. How am I gonna have this ring get my answer? And then you cry a little bit. Yeah, it's like that. Some minerals can be identified by special physical properties. Calcite bends light to produce double images, as shown in Figure 9. Other minerals conduct electricity, glow, when placed under ultraviolet light, or are. Alright, Ms. Reams, gotcha, but how do minerals form in the first place? I got your back, kid. On a rock collecting field trip, you find an egg-shaped rock about the size of a football. That sounds like a fun field trip. Later, at a geologic laboratory, you split the rock open. The rock is hollow. Its inside surface sparkles with large amethyst crystals. Amethyst is a type of quartz. You have found a geode, as shown in Figure 10. A geode is a rounded, hollow rock that is often lined with mineral crystals. Geologists believe that crystals probably form inside a geode when water containing dissolved minerals seeps into a crack or hollow in a rock. Slowly, crystallization occurs, lining the inside with large crystals that are often perfectly formed. Crystallization is the process by which atoms are arranged to form a material that has a crystal structure. In general, minerals can form in three ways. Some minerals form from organic processes. Other minerals can crystallize from materials dissolved in solutions. And finally, many minerals crystallize as magma and lava cool. We know that all minerals can form by inorganic processes. However, some minerals also can form by organic processes. For instance, ocean animals such as clams and corals produce shells and skeletons made out of the mineral calcite. Hey, pause, look at this. Down here at the bottom, we've got our geode. That means they have this giant rock that doesn't kind of look pretty on the outside, but they chomp it in half, and they went, now you have two halves of this rock, and you can see crystals forming on the inside. This has complete the graphic organizer to show how a geode forms in 4 steps. Cool, I got you. First step, a crack or hollow forms in a rock. Duh. Then what do they say happened next? Well, probably water that contains dissolved minerals seeps into the crack or the hollow in the rock. But then what? Oh man, you'll never guess. Crystallization slowly occurs and it lines the inside of the rock with large crystals. But then what, Miss Reams? And then, kapow, you got a geode. Sometimes, the elements and compounds that form minerals can be dissolved in water to form solutions. A solution is a mixture in which one substance is dissolved in another. When elements and compounds that are dissolved in water leave the solution, crystallization occurs. Minerals can form in this way in bodies of water on Earth's surface, but the huge selenite crystals shown in Figure 11 form from a solution of hot water that cooled underground. Some minerals form when solutions evaporate. For example, when the water in salt water evaporates, it leaves behind salt crystals. In a similar way, deposits of the mineral halite formed over millions of years when ancient seas slowly evaporated. Such halite deposits are found in the American Southwest and along the Gulf Coast. Gypsum and calcite can also form by evaporation. Sometimes gypsum forms in the shape of a rose. Picture of a gypsum rose. Deep underground, magma can heat water to a high temperature. The hot water can dissolve the elements and compounds that form minerals. When the hot water solution begins to cool, the elements and compounds leave the solution and crystallize as minerals. For example, quartz can crystallize from out of a hot water solution. Pure silver is also deposited from a hot water solution. Gold, too, can be deposited in this way. Pure metals that crystallize from hot water solutions underground often form veins. A vein is a narrow channel or slab of a mineral that is different from the surrounding rock. And then let's ooh and ah over AG, silver. Hey, and then down here at the bottom, look at the sky. The sky is a huge selenic crystals in a cave in Mexico that formed from the crystallization of minerals in a solution. But anyway, I'm just wanting you to look at the fact that these things are huge. This guy is standing next to one and in front of one. And if he laid on the one that's like going up kinda, he wouldn't even be the size of it. Assuming that this guy is probably a typical guy who's at least 5'9", 5'10". These are like pretty huge. Many minerals form from magma and lava. Minerals form as hot magma cools inside the crust or as lava hardens on the surface. When these liquids cool to a solid state, they form crystals. The size of the crystals depends on several factors. The rate at which the magma cools, the amount of gas the magma contains, and the chemical composition of the magma all affect crystal size. Magma and lava are often rich in oxygen and silicon. Many minerals that contain these elements are called silicates. Together, silicates make up the majority of Earth's crust. Minerals from magma that remains deep below the surface cools slowly over thousands of years. Slow cooling leads to the formation of large crystals. Quartz, feldspar, tourmaline, and mica are common silicate minerals that form from magma. And there you have a picture of tourmaline. It's so cute. I love that purple one. Minerals from lava. If magma erupts to the surface and becomes lava, the lava will cool quickly. There will be no time for large crystals to form. Instead, small crystals form. Leucite and olivine are silicate minerals that can form in lava. Look at you, olivine. You definitely look olive. Hey, Figure 12 says minerals can form by crystallization of magma and lava or by crystallization of materials dissolved in water. So which minerals are formed by evaporation? What? We said halite, gypsum, and calcite. Which mineral can form in hot water solutions? We said selenite, silver, gold, and quartz. Minerals formed as lava cools? We said leucite and olivine. And minerals formed as magma cools? We said quartz, feldspar, tourmaline, and mica. Whoa, hold up a second. Quartz is on here twice. Get on their level. Earth's crust is made up mostly of the common rock-forming minerals combined in various types of rock. Less common minerals are not found evenly throughout the crust. Instead, several processes can concentrate these minerals or bring them together in deposits. An ore is a deposit of valuable minerals contained in rocks. Iron ores may contain the iron-bearing minerals pyrite, magnetite, and hematite. Lead ores may contain galena. These ores are mined and the iron or lead is separated from the rock. Graphite and sulfur are sometimes also mined. Figure 13 shows some major mining areas. It says copper, aluminum, or if you want to make my mom mad, aluminium. zinc, iron, and nickel can be used in making fridges. Which of these metals might the United States need to import for its refrigerators? Well, where do we not have? And we're looking for copper, aluminum, zinc, iron, and nickel. Gotcha. Which of these shapes do we not have in the United States that we're going to have to knock on other countries' doors and say, please trade for me? Alright, your time is up. You could have paused the video at any point to try and figure it out yourselves. The answer is aluminum. We do not have a little tiny orange triangle anywhere in the United States. Iron. We don't really have any little boxes. There's one like straight up top in like, I don't know, Wisconsin and Montana area, but that's about it. Probably should just go ask somebody else. Nickel, we do not have any yellow triangles near us, so there is one that looks like it is just across the border in Canada, and we can just knock on their walls or doors. Whatever. You know what I mean. Alright, that's all I have for you today. We classified some minerals, my dudes. Tomorrow is social studies. Sweat in the bag. Gotta love that, social studies. And then we're going to be talking about how can we classify rocks. What's the difference of classifying a mineral and a rock? How do we do that, Miss Reeves? I got your back, kid. We'll do that on Monday. Have fun. See you then.